Seeing an airship floating is a rare sight. Only a few of these graceful giants exist. They use a gas which is lighter than air to stay afloat. As it comes into land, you can see how easily the wind pushes it around. It's the job of the ground crew to grab the tow ropes and help guide it across the airfield. They have to hold on tight, literally stopping the whole thing from floating away. The idea of a lighter-than-air craft has been around for a long time. Before aeroplanes were invented, the first commercial passenger aircraft were airships. The R100 was 215 metres long and one of the first to carry passengers across the Atlantic. It was a huge structure, a rigid metal framework covered with fabric and filled with hydrogen gas. With a spacious interior, passengers enjoyed the same sort of luxuries as those aboard ocean liners like the Titanic. They really were ships of the air. So why did they never become a popular form of transport? This party balloon is full of hydrogen gas. Just like helium, it's lighter than air. But see what happens when a naked flame approaches. Hydrogen is light, it's cheap and readily available, but unfortunately, it's also highly flammable. As the Hindenburg airship came into land in 1937, it caught fire with fatal consequences. 35 people died. An alternative gas which doesn't burn had to be found. These bubbles are full of hydrogen, and although they're light, they easily catch fire. The gas in this bubble is carbon dioxide. It's far too heavy. It won't catch fire, but it'll never get off the ground. This gas is light and doesn't burn. It's helium. Although it's the best alternative to hydrogen, helium is very expensive. It costs £6,000 to fill this three-seater craft, which is probably one good reason why airships are so rare. Every few days the helium needs topping up. It's piped from portable tanks into the airship through a nozzle in its nose. The helium gives the airship lift. Too much lift and it would be difficult to control the airship, so it needs weighing down with bags full of lead. Once up in the sky, the airship floats in an ocean of air. But how does the airship keep its shape? All gases are made of particles. The particles have a lot of energy. They move around and spread out. Gases don't have a fixed shape. They simply take on the shape of their container, in this case, the envelope of the airship. Helium particles bombard the inside of the envelope, but the airship is surrounded by a gas on the outside too. Air particles are constantly striking it. These moving particles create a pressure. Helium pushes on the inside while the air pushes on the outside. But the pressure inside is slightly bigger, big enough to keep the whole thing inflated. What would happen if the helium leaked away? Gases are used to inflate all sorts of things. The gas blown into these inflatables takes on the shape of its container. The more gas that's pushed in, the more particles there are pushing against the inside of the container, and the firmer it feels. The pressure inside the beach ball is greater than the pressure outside, just like the airship. A bicycle tyre needs to be very firm. The more air that's pumped in, the higher the pressure inside. So, what happens if you open the valve? The gas in the tyre escapes until the pressure inside is the same as the pressure outside. Gases always move from high to low pressure. To support this truck, a huge amount of air is forced into each tyre, but it's a slow job. Being able to inflate an object quickly can be very important. A small container of carbon dioxide gas under high pressure is enough to fill a life raft big enough to hold 10 or more people. As soon as the canister is opened, the gas escapes into the raft. Again, it's moving from high to low pressure. All that gas out of this small canister. This life jacket is full of gas. So, what will happen if even more is forced in? Why does a life jacket burst? Air is the most common gas of all. Blow into a balloon and it easily inflates. The question is, will a full balloon be heavier or lighter than an empty one?
This one is definitely the heaviest.
I think this is the heaviest one.
This deflated balloon has a mass of 2.1 grams. Inflate it, and how much do you think it'll weigh? It now has a mass of 2.6 grams. Each tiny air particle in the balloon has a mass. One particle on its own doesn't weigh very much, but a balloon contains many millions of them. So, a full balloon always has more mass than an empty one. The property of gases is that they can be squashed or compressed. Compress the air inside this sealed syringe, let go, and the air expands, pushing the syringe back up. Particles are spread out. It's easy to squash them closer together. But release the pressure and the particles immediately move as far apart as possible, pushing against the syringe. Compressed gases can act a bit like springs. This awesome ride at Blackpool Pleasure Beach uses compressed air to catapult its riders to a height of 65 metres in just 2 seconds. As soon as the passengers have been safely harnessed in their seats, their combined weight is measured. It's like a big set of scales. The greater the weight, the more compressed air it takes to launch the riders to the top of the tower. The air is forced into a tank and held under pressure, and then it's ready to go. Other fairground rides use compressed air too. The braking systems of many rides rely on air to stop the cars. You can hear the hiss as the compressed gas escapes. What other vehicles have air brakes? Under normal conditions, gases take up a lot of space. During the Second World War, some cars were converted from running on petrol to running on gas, carried in huge bags on the roof. But it's difficult to carry large quantities of gas like this from one place to another, and let's face it, it looks stupid. Today, gases are transported in high-pressure cylinders. The equivalent volume of 300 cylinders of normal gas can be forced into just one by compressing it. So the cylinders need to be extremely strong. All sorts of gases are stored and transported in this way. Different gases have different uses. Carbon dioxide gas is used to put the fizz into fizzy pop. But how did it get there, and just how much gas is there in a bottle of pop? The gas arrives at the pop factory in huge tankers as liquid carbon dioxide. When CO2 is cooled and compressed, it liquefies and takes up less space. So, 700 tankers worth of gas can fit into just this one. In a totally different part of the factory, the cola drink is being prepared. All the ingredients are mixed together in huge vats. The liquid carbon dioxide is transported around the factory through a network of pipes. It's heated up, turned into a gas, and injected into the flat cola mixture. The bottles are filled and capped immediately to keep the fizz in. Because gases are so compressible, it's possible to squash the equivalent of 8 litres of carbon dioxide gas into this 2-litre bottle of pop. This factory produces 1,500 cans of pop and 250 bottles every minute, so you're talking about a lot of fizz. Just think how much carbon dioxide is trapped in all these. We rely on one particular type of gas to keep us warm, cook our food, and even heat things up in the lab. Natural gas is found deep underground, and its chemical name is methane. The gas is trapped in rocks many thousands of meters below the seabed and is brought ashore by underwater pipes. It arrives at one of 6 coastal terminals. When it comes ashore, natural gas doesn't smell. The gas company Transco makes it smelly on purpose, so it's easy to spot a leak. They add an odorant which contains some of the smelliest chemicals on Earth. From here, it makes its long and winding journey around the country. A massive network of pipes transport natural gas throughout Britain. Most of them are hidden underground, but sometimes you can spot their course from the air. Lay them out end to end and they'd be long enough to reach around the world 6.5 times. In towns and cities, huge gas holders store the gas at low pressure. It's ready to use and close to where people live. Scientists are continuously checking the gas to make sure it's safe. This man is known as a calibrated nose. His sense of smell is extremely sensitive. It isn't exactly a run-of-the-mill job, but just by sniffing a small amount of gas, he can tell whether or not it smells too strong or too weak. It's vital that it smells just right, so that any leaks can be spotted straight away. Natural gas burns easily and cleanly and gives out a lot of heat, which is what makes it so useful. But its flammability means it can also be dangerous. Thankfully, sites like this are rare. But an uncontrolled escape of gas can be fatal. Mixed with air, the gas can explode. So it's always important to report any sign of a leak.
Good afternoon, Transco Emergency Service. How may I help?
Hi, I think I can smell gas.
Where are you smelling?
Transco's hotline receives calls from the public 24 hours a day.
Kitchen, I think. I'm not sure really.
We'll have an emergency engineer out to you within 1 hour.
Hi, good afternoon, Transco. I believe you've reported a gas escape.
I did, thank you for coming.
This way.
The engineer has an electronic probe. It immediately measures how much gas is in the air. A reading of above 20 and it's time to evacuate the building. There doesn't seem to be any sign of danger. The gas seeker is only registering 0. But that doesn't stop the engineer from carrying out a full sequence of checks. Every call out is taken seriously. Only when the engineer is completely satisfied that there isn't a gas leak and the house is safe will they leave the home. In the past, rotten cabbages and creosote have thrown investigators off their scent. How good is your sense of smell? And what smell would you use to warn people of danger?
My favourite smell is chocolate.
My favourite smell is fish and chips.
My favourite smell is toffee.
I hate the smell of the subway.
My worst smell's mustard.
Pizza. Fresh fruit.
I like the smell of roses.
I hate cabbage.
I just hate the smell of onions.
I love the smell of chocolate.
We're surrounded by different smells every day. Some we like and some we don't. These investigators are sniffing manufactured smells.
Quite nice, is that?
But what makes something smelly? And what has it got to do with gases?
Oh, that reeks.
Imagine you can see what's happening to the particles. Smelly substances release some of their particles into the air as a gas. Particles are escaping from this liquid. As they diffuse through the air, some reach his nose. Messages are sent to trigger a smell response. So, for something to be smelly, some of its particles must have enough energy to become gaseous and get up your nose. If you smell dead fish, there must be dead fish particles up your nose. Yuck! This body spray is designed to be smelly. Give it a squirt and a fine spray of liquid is released, but it quickly changes into a gas. To find out how quickly these body spray particles mix with the air and spread out, we have a team of smell detectives equipped with blindfolds so they can't see what's happening, and white flags to lift when the smell hits them. Standing at varying distances from the source, they're ready to do some serious sniffing. How long will it take for this smell to diffuse through the air and reach the back row? The gas particles reach the first row after just a few seconds, but it takes quite a while for the second row to react. The smell is obviously taking longer to reach them. Why does it take so long for the particles to travel long distances? What's stopping the body spray particles from reaching the second row for so long? Manufacturers always boast that their body spray is the one that will turn people's heads in the street. But can the smell really travel that far? Do all smells behave in the same way? To compare two different body sprays, how would you make your test fair?